Okay, we're live. Welcome to another session of discussion on for our Assumptions of Physics project. Today we have a student that came that contacted me because he had a bunch of questions on essentially mathematical foundations of quantum mechanics. We chatted a little bit, and then I realized that I think those questions could be of general interest, and I do want this space to also be open for people that might want to come and discuss things more in detail. So I invited him here, and he's here, Robbie. And so
Hello.
we'll start with the questions that he has, and we'll see how it goes. And if people have questions, please do put them in the chat. So please, Robbie.
Okay. Yeah, and as a disclaimer, I'm far from an expert on quantum mechanics. I am early in my journey of learning this stuff, and I think I'm finding it kind of unsatisfying, which I think Gabriel had a similar experience when he was first learning this stuff, and I hope he can give me some good pointers.
Exactly. Hoping that some of the things that I learned can help you and other people. So
Mhm.
fire away.
Okay. So my first question is on the distinction between wave function and state vectors. So it's commonly said that they're both elements of a Hilbert space, but mathematically they're fundamentally different objects, with wave function being complex valued functions of, say, position of or momentum, and state vectors being something more abstract that may be projected to a wave function through like a position or momentum basis projection. Um, so my question is a state vector a more, does a state vector describe a quantum state more thoroughly than a wave function?
Okay, so there are three things I would say that we should distinguish. So the wave function typically is the function, like the complex function, let's say, on position. And not all wave functions are distinct vectors in the Hilbert space. So you could have, imagine this, imagine that you have a wave function like a Gaussian state. And
Mm,
then you change the value at a single point. So you take, I don't know, the center, and instead of having the peak, at that point, you set it to 0. Now, technically, the wave function is different, but whenever you're doing the inner product, whenever you're doing integrals, the fact that you change the value at a single point does not matter.
mm.
So when you do the state vectors, when you're actually looking at the Hilbert space, the Hilbert space is the equivalence classes of all the wave functions that sort of are indistinguishable through the inner product.
So with like a a phase, a different phase, you would have still have
No, because
the
the
same.
phase gives you a different function.
Mm,
So then there is the third thing, which is the ray in the Hilbert space, which
mm.
is taking the vector and quotienting out, removing the absolute phase. And that's yet another equivalence class. You see, this is a complete madness, the way this is set up. So you have the wave functions. Again, the wave functions are, let's think it even non-complex. It would be a lot easier. So think of just classical probability distributions, right? If you change values on a set of zero measures, so a point, countably many points, all the integrals are going to be the same. The probability is actually the same, right? And so those would be the state vectors. All those functions that when you do integration are the same, then they become the state vector. And it's the vector in the Hilbert space. That still has the phase information in quantum mechanics. The phase information is removed when you do the projection, like when you go in the projective space. And the projective space is really taking the vectors and making another equivalence class of all the ones that are sort of the same, apart from a phase and a different magnitude,
Mhm.
right? And so those are actually the states. Those are actually the physical states. Because if you have a
Um,
in the state vector, we are changing only the magnitude or the phase, you have the same state. And if you're changing the wave function in some points, but you're not changing any integral, then you're not changing anything in the inner product, therefore you're not changing any of the probability, then it's still the same anyway.
So are you saying we could have different wave functions for the same state vector?
Yes.
Okay. And so you can have a array in a Hilbert space and have different magnitudes of the vector.
Yes.
Is that correct? That part always confused me because what about the normalization condition?
Right. So the normalization condition is essentially is not there. So in the Hilbert space, vectors are not normalized. You can have whatever magnitude that you want. In the projective space, there is no sense of norm. There is no magnitude because the magnitude is stripped away in the same way that the phase is stripped away. So the reason why you normalize the wave function is because when you have normalized vectors, right, then it's closer as a one-to-one map to the number of to the states because the states are these elements of the projection of the projective space where you removed the magnitude. So it's a little bit like if you make the analogy, which all these names come from analogy in real space. So you have three-dimensional space. All the vectors are sort of, let's say, distance from the origin. And then array is basically a line from the origin out, right? Actually, it's called array, but it's actually a line that passes through the origin. So the array is actually going in both directions. And that would be, let's say, the state really, right? This line that goes through the origin. And then, of course, if you take sort of the part of the sphere, then you're going to have one element. If you have the sphere, you would have all the elements with unit distance. And then, for every ray that you would have this intersection with the sphere. With the technicality that you don't have one intersection, you have two intersections at the 2 points. So you technically have a half a sphere, not the full sphere, but that's another thing that makes the thing a little bit complicated, more complicated, but yeah.
And then go back to projection space. So I get the idea of projecting a projective space.
Yeah.
Is there something distinct from projecting a state vector onto a position basis?
So there you don't project into a position basis. You make a representation in the position base. Like you make a decomposition in, well, position base doesn't technically exist, but let's say that we make a representation in position, yes.
But say you can project to like a number basis, for example. Is that an actual projection?
You might have, like if you have a space with variable number of particles, then you would have that would be an actual base. You would have a base, a set of vectors, one for each possible number of particles, yes.
Okay. Because I see the definition of, or I don't know if it's the definition, but like writing a wave function in the Dirac notation, it's written as a projection onto like X, for example. Like you have X psi.
Right. So I should have set up this beforehand. Let me see if I can set up my tablet so that we actually have a whiteboard to write on. Let's see. Okay, so I need a new document. I need to open up Zoom here, if I can find it. I need to join the meeting.
So we were talking about projective space of a Hilbert space?
Yes.
Okay, I guess I'm I did a bachelor's in math. Sometimes
No,
the math,
I know
yeah.
it's kind of interesting because so I also I studied this thing through the physics route, right? And like there were so many things that were sort of vague and didn't make sense to me. And it's
Mm,
only when I essentially by myself, because I wanted to, I started looking at the mathematical detail. Then things started slowly to click. And I do think that it would be a lot more useful to just have, in any class, a couple of lecture to these things so that one has a clear idea what's going on. But I don't even know if most physicists that actually, work like they don't really work on foundation, they just make their calculation and so on, actually would be, they would know all these things, quite frankly.
mm,
Because I see when I write papers and I talk to people and I see the reviews that I get from the paper, I even see that the people that are making the reviews are confused themselves.
yeah,
And
yeah.
there is the absolute problem is that it's like the physicists are confused with the math because they sort of use it in a sort of way that it's not absolutely precise because in some cases the math is hard, and so that's kind of understandable. But then the mathematicians that do know the math are not so clear on how it maps to the physics. And then things sort of get I mean this is my whole interest in this line of research, is that there are things that are getting lost in the translation, and yeah, and that's the absolute problem. So you were saying when you make you wanted a position basis, you basically write stuff like this, right? This is what you were talking about.
Yeah.
Okay, so technically this is problematic
Mm,
because these things here are actually delta Diracs, right? It's things like these, and these are not elements of the Hilbert space.
they're elements of a rigged Hilbert space.
They are elements of the space of distribution. So you have the Hilbert space, you have the Schwartz space. The Schwartz space includes all the functions that basically you can think it like this. The expectation of any polynomial of position and momentum is finite.
Mm,
And so this means that if you imagine in X, the the function has to go at infinity faster than any polynomial, essentially like an exponential. It has to go down fast, which means that the particle has to be, or the state has to be very well localized, otherwise it wouldn't be there. And let me get, oh my God, I think, okay. And then it has to be infinitely smooth because now the nth derivative in x has to exist.
mm,
And so it's the short space is the space of um, um, essentially space of wave function, or a space of function that it's infinitely smooth and goes down to infinity like an exponential. Now this space has a dual space. And what is the dual space? Is the space of all the linear functions of the original space. And if you ask what is the value of the function at a particular point, that's a linear function. Because if you take the sum of the two functions, then the value is going to be the function and so on. And so the delta Dirac is in here. Like it's not in here, but it's inside here. The delta Dirac is in there. And so
Is
it's not
that
in the, Go
My
ahead.
idea, my my idea of dual space for Hilbert space was like the space of bras, where they mapped the kets to a complex number.
Right. So uh, in the Hilbert space is self-dual. So
Hmm?
the space of linear functions of the Hilbert space is equivalent to the Hilbert space itself.
Yeah.
That's why a lot of mathematicians like the Hilbert space, because now you can have this representation. You can have an inner product and say that you have two elements, right? And
Mhm.
now this x dot, right, this thing is going to be a linear functional over y. So instead of writing the inner product like this, like we do in physics, right? You can imagine now, well, let's say phi m psi. You can think of this as this applied to phi. So if you
Mhm.
just put the bra on one side, then you can understand the bra in the inner product as being a linear functional over the space itself, right? So mathematically, you can say, oh, these two things are the same. And
Is there the same correspondence with a Schwartz space and its dual?
yes, but you can't really make it as an inner product in the same way that you would have it, because what would happen is that not all the functions can be represented as coming from the inner product of the function themselves. So to me, here is exactly one of the misidentification that is happening between math and physics. When we think
Mhm.
of this, right, we typically think in physics, we think that as the out state. This is the in state, the psi is the in state, and this is the out state. And this is basically the square root of the probability of going from the in state to the out state.
Mhm.
Right? That's how we physically think about it. Right? And what the mathematician wants to think about, the way that they are more encouraged to think about it because it's useful and so on, is that this is an element of the, oops, it's an element of the state, of the space, and this is a linear functional,
Mhm.
right? And this does not work in physics. Like that's the out state. So what happens is that when you're in the Hilbert space, whether you're talking about elements or linear functional of the elements, doesn't matter because
Mhm.
it's self-dual. So if you get one or you get the other, it really does not matter. And the point is that that the thing that we discuss in our unphysicality of the Hilbert space, the Hilbert space itself is too big because it contains all the states for which this diverges.
Mhm.
And so not all these elements make physical sense. And if that's the case, then you have to choose, okay, what am I going to, when I'm making this pair of the inner product, what is it that I'm trying to describe? Am I describing some relationship between two states, or am I describing some relationship between a state and a function? And physically, the correct answer is it's relationship between two states. And I think that's where we don't quite have the correct math.
Um,
Very
so
confusing.
yes.
Let me get a question. There is a question from the chat. Mars asks, since the nature of quantum mechanics is probabilistic, the assumptions of classical mechanics, determinism and reversibility applies on quantum mechanics. So yes, it applies when you're doing a deterministic and reversible evolution, in the sense that the determinism and reversibility at that point does not apply to the elements of the distribution, but applies to the whole distribution. And so you are mapping one wave function. So you're mapping one wave function, right, at t0, oops, to another wave function at t1, and you have a one-to-one map. And you have a one-to-one map that moreover preserves the inner product, which means preserves all these probability of transition, which means that all the, let's say, all the probabilistic part, it remains conserved anyway, such that if you had the two states that had a particular probability of transition and you evolve them, they still have the same probability of transition. And so in that sense, the evolution in quantum mechanics, the Schrödinger evolution, the unitary evolution, is still deterministically reversible. But when you then make the transition through measurement with the probability of transition like that, evolution breaks the assumption of deterministic and reversible evolution. That's not going to be deterministic. So if you come with a spin up and you measure spin in the horizontal direction, then you're going to have an outcome left and right, and that evolution is not deterministic. But it's the same thing in classical mechanics. In classical mechanics, you have Hamiltonian evolution, that it's absolutely deterministic and reversible at the level of the microstate. But then you can have other determination. You can have stochastic processes. You can have dissipative processes. Those are not going to be deterministic and reversible in exactly the same way. So that's where the difference is. So again, the way that I think of all this thing is that you have a set of states, and then you have different types of evolution that you could have, depending on the case that you are describing. So I hope that makes sense, Mars. And we can go back to your question, Robert.
Okay, so the position representation can be done without having position eigenstates. Is that correct?
Right. That's basically what's going on. So the way that you think of the position representation is that you have your in the abstract, you have a wave function, right? And you are sort of you're using essentially this delta Dirac to get out the values, but it's not really technically doing an inner product between with a basis. And one of the things that gets confusing is that, again, people would like to think of these as states. So you write them in physics, you write them because sometimes you can pretend that they're states. But one of the things that where they fail completely and where people get confused is when you do now a unitary transformation on these states, they don't they change fundamentally because they are not really states, right? A vector in a Hilbert space is a vector in a Hilbert space, and it's always a vector in the Hilbert space. But when you make when you take a delta Dirac, and for example, let's say you make a unitary transformation such that you shrink the space. So you go from x to, let's say, 2x, right? So you're shrinking or stretching the space, right? So this is a completely a linear transformation in X, and it's also a unitary transformation in the Hilbert space. But what's happening is that this X here is not going to be the same as the X here. There's going to be now I don't know if it's a 2 or a 1/2. I would have to go and work the math out. But this is different. They are different. Because what happens, again, if you imagine the delta Dirac as a distribution that it's very fine, right? And this is integrating to 1. If you stretch it, right? You stretched it, now this is going to integrate to 2. And so what happens is that to make it integrate to 1 again, you have to bring it down.
But isn't it like infinity at zero?
Yeah. It's still gonna be infinity, right? But
Yeah.
uh, the problem when you make things go to infinity is that you still need the understanding that there was a limit of some sequence,
Hmm.
right? And so it's this is where infinity is not really always equal to infinity. Like there are these subtle issues. And uh, and so if you want to get, or another way to think about it, think about in terms of operator, right? So imagine that I had, I have my wave function, right? And I say, what is the value here? Well, the value here is going to be, let's say 1. I stretch it, and now the value here is going to be, let's say, 1/2, right? So if you think as the delta Dirac as the function in the abstract that was taking this array of the Hilbert space, which is defined in a way that doesn't care what the representation is, right? You see that I'm getting a different value. And so if I'm getting the different value, that delta Dirac in the two cases can't be the same thing. Because if it's the same operator acting on the same state, you would get the same value. But when you are changing the position representation because you're stretching x, you don't get the same value, you get something lower. And it's still because these delta functions are not elements of the Hilbert space. And therefore, what we write here as being a part of the inner product, it's not really the inner product that is defined on the Hilbert space. Because yes, this is an element of the Hilbert space, but this is not an element of the Hilbert space. So that object that we have there, that inner product that we're using, it's not the same inner product. And so we're not guaranteed that when we're making this transformation, that inner product is preserved. Because the unitary transformation is going to require that the inner product in the Hilbert space is preserved, but it's not telling you anything about what happens for the inner product of the Hilbert space and the space of temporal distribution as star.
Mhm. So is the issues with the position eigenstate, is that characteristic of eigenstates of all unbounded operators?
Not unbounded, it's dense. The problem is density. So if you had, let's say, the Hamiltonian for a harmonic oscillator, right? That's unbounded. It's bounded from below, but it's unbounded from above, right?
Yeah.
But the spectrum is discrete, right?
Yeah.
You have you have your jump operator, your ladder operators. You go up, and you can go down.
Mhm.
Those eigenstates of the Hamiltonian are actually elements of the Hilbert space.
Mhm.
And you see they're countably many, and they form a complete basis. There you don't have a problem. When you do the unitary transformation, everything works fine. Now, if you have something like the Hamiltonian for a hydrogen atom, right, where you have some bound state, but then you have the unbounded part, and the unbounded part is actually continuum, like the spectrum is discrete below the threshold and is continuum above, you would not have the problem for the eigenstates below, but you would
Mhm.
have the problem on the part that is continuous above.
Okay. Yeah, that makes sense. Yeah, and I was thinking about um if the size of a Hilbert space is defined by how large a or basis is that spans it,
Right.
then the continuous case, if you have a continuous basis and a discrete basis, then there's a
Right. That's
discrete.
really the point, is that you can't have like a continuous basis does not work
Mm.
because the Hilbert space that we work on is the dimension is countable. And so
Mm.
there is no such thing as an uncountable basis in the Hilbert space, because if you have a vector space, the fundamental property is what is the size of the bases. And if it's infinite, it's either countable or uncountable, well, or the continuum or some other cardinality. The cardinality has to be fixed. So it can't be that, if your Hamiltonian has a discrete spectrum, you're countable, but then if your Hamiltonian is a continuous spectrum, you're not countable anymore. No, it's always countable. And
It's always countable.
it's always countable. And so it shows that you have a problem when you're trying to make a base in position because you're trying to make sort of an unaccountable basis, and that just doesn't work.
Mhm.
Okay, I have another question from the chat.
Yeah.
Have you seen, from Magma, have you seen the stochastic quantum correspondence? It provides justification for Hilbert spaces to be used in quantum mechanics by showing that the Hilbert space are equivalent to stochastic mechanics. So this is kind of it's very similar in the sense that you're looking at the space of probability distributions, but you have the same exact problem in classical measure theory stochastic processes that if you want to make your probability distribution are going to form a space that it's separable, that has a countable basis. And the fact that you use Hilbert spaces because you're trying to complete things. So in classical mechanics, you can imagine that you're trying to, again, put these Dirac measures inside the space, and the Dirac measures are essentially the counterpart to the Dirac function for measure theory. And so all these problems are related, and they're problems that we're trying to find like a good characterization, general characterization, such that when we can talk in general about the correct space of ensembles. And there are some parts that come from the topology, some parts that come from the measure theory. And that's sort of the part that I'm still trying to figure out exactly what is the right math that maps to the correct physics. And that part it still escapes me. I don't have a final answer on that. Could the algebraic number work instead of the real numbers for continuum-like spaces with a countable amount of elements? I don't think it's a problem of the points. So this is kind of where I think our intuition from discrete spaces, it's kind of leads us in the wrong direction. So you can imagine that I have space X and then I have all the set of probability distributions, right? And whenever we measure X itself, we're never going to measure a single point. We always measure essentially open intervals. And that's what gives us the topology of the space. The fact that the points are really throwaways. The points don't really exist. What we measure are little areas. And then we say, okay, in this little area, I have this probability or this many possible states that I could have. And so the function that we have, like even when we draw this typically, the correct way to think about it in terms of measure theory is in terms of set functions. So instead of saying I have a probability density at a point, that's not how probability works. Probability works that you have a measure that takes a set, right, from X, and this sigma is the sigma algebra that are basically subsets of X. And then for every subset, you give a number from 0 to 1. And in the same way, it works the same way for volumes, right? If you think about it, we never measure, we never measure mass densities or charge densities. What we always have is a finite region U, and then we say, oh, what is the charge? Let's call it C. What is the charge that is in U? And then we get a number, a real number, a positive, well, positive, negative real number. Or we have a mass, and we think about, well, there is a mass, and we get, in this case, a non-negative real number, right? This is what we do when we do physics. Those are the things that we are modeling. The fact that then I can say, oh, I can think of the probability as actually a density over a point, or my charge as a charge distribution over points and so on. Those are things that we think about, are models that we construct where we can imagine that we can take these limits of regions that are smaller and smaller and smaller and smaller. And then we say, aha, now we have a ratio between the volume and the charge, or the probability on the volume, or the mass on the volume. And that's how we define densities. The density is never a prime physical object. It's really derived. So if we imagine, for example, that there is some physical reason why you can't always make this volume smaller and smaller, or even the charge, when you make it smaller, like when you make a region smaller and smaller and smaller, you start having problems actually detecting smaller and smaller in charge, then that limits that it's in your head mathematically. It's not something that it's implementable more in the physics. And so if you want to be technically correct, you say, okay, well, if I can't make that sequence in practice, then that limit does not exist physically for whatever reason. But then if the limit does not exist, cannot exist physically, the thing that still exists are all the finite measurements of finite regions, of finite volumes, of finite probability. Those are the things that we measure. So those are the things that are primary. And so the fact that we're trying to think about that there are points and so on, that's the limiting thing. That's the thing that sort of technically does not exist in physics. We're not going to be able, for example, to make a probability measure that it's a Dirac, that we always prepare with 100% precision a particle at exactly the same point with infinitesimal precision, right? We can't do that. So those objects technically do not exist. Now, of course, it's convenient to think that there are points and we have distributions, and so that's why we do it. It's a useful model. But the problem is taking those things too literally. And I think that's the problem that happens with Hilbert spaces and other mathematical constructs, that we're trying to make those things too literally, and then we start running into a bunch of problems. And I think what helps is being clear what your assumptions are physically and how they map to the math, such that then we can have a careful map between the two things. So this is a very convoluted explanation. I hope it makes sense, Magma. I hope it makes sense. Rob, wanna go back to what we were discussing?
Can I ask something?
Oh yeah, Tobias,
Can you
please.
hear me? Okay. So in trying to figure out what the position representation thing, how it works.
Mhm.
So if we use tempered distributions, we can at least make sense of the bra vector, but we cannot make sense of the ket, right?
The problem
So
is the inner product. So you can make sense of of this of the x as being a part of the tempered distribution, and psi as part of the Schwartz space, right? The problem is that the inner product between the two is technically not the inner product that it's in the Hilbert space. It's another inner product.
okay, wait, but I was thinking about the bra x psi as not an inner product, but just like an evaluation.
Oh, okay, yes.
So then x then the bra vectors are in our tempered distributions, and then the kets would be Schwartz functions.
Right. You would write something like this at that point. You would not even have an inner product. You say this
Yeah.
part is inside S star, and the psi is a part of S.
Yes. So and then if people want to denote that differently, I'm fine if they just write it in terms of brackets. But still, then I could not write an x vector, because there would be an element of like a Schwartz function, and there is no Schwartz function, which is an eigenstate of position operator. Is that right?
Right, but then you also have the problem that you're changing the meaning of what you get out. Because what you get out here is not a probability, but a probability density.
Mhm. Because the Dirac delta needs some kind of notion of density.
Oh, it already has the notion of the density.
Yeah, it's
Right.
by definition, it has some notion of that. Yeah, okay.
Because it's
But still, I just want to make sure we talked about some things working out, but we cannot mathematically well define this properly.
Oh no, you can define this properly. That's not
This,
you can.
but not the full thing, and like to write the psi as like an expansion of position eigenstates.
Right.
That never works, right?
You can't write it like this. If you start writing it like this and treating these things as Hilbert, as if they are exactly the same thing as elements of the Hilbert space, that's where you bump into problem.
But I can at least define something like this that makes mathematical sense.
Yes,
As in, it is an evaluation of a tempered distribution.
correct.
I can at least define this mathematically.
Yes.
But I cannot even mathematically define then what an eigenstate of position operator is, right?
Right.
So the full expression,
yeah.
yes. So that even mathematically will be impossible, even though, so there's no chance to even cook something up.
Well,
While
again, it depends on what you mean by eigenstates. If by eigenstates we mean elements of the Hilbert space, so that when you are, when the position operator acts on them, they remain unchanged or remain the same up to a multiplicative constant. No, that those things don't exist in the Hilbert space.
But then you would expand state as distributions.
Right, but
that would
that's
make
exactly
no
the
sense,
problem.
right?
So you could say,
yeah, okay,
right? So these two things, right? The Schwartz and the dual are dual, right? So the math is not going to tell you which ones are the states and which one are the operators.
okay.
Okay, so you could say, so the operator X, right? You're gonna find it both in the it's not a Schwartz. No, it's not an element on the Schwartz space. Okay, so then you probably are not gonna be able to do it. Both the X and the delta are in the Schwartz space. So no, okay, I stand correctly. I don't think you can do it because both the operator X and the delta Dirac are both only in S star, right? X is going to be here. And so you're not going to have a position operator on the dual. So, okay, I don't think you can do it. That in a way that it makes sense.
So yeah, how do we actually formally discover that we have wave functions if you would start only from an abstract Hilbert space and have something like a position operator? I guess people, I don't know, find like representations of I don't know, 1D would be just translations, but like I guess in general relativity would be like the Poincare group or something like that. And then would there be like a technical way to find out that my elements actually can be described somewhat like wave functions? So I'm just curious because here it seems like the abstract Hilbert space is an L2 of some specific geometric space, right? So we kind of built that in from the start.
Yeah.
But if you would not do that from the start, how would you find out, my actual Hilbert space, why can't I think about it as an L2 of R3 or something like that?
Right. So you need some. So if I just give you the Hilbert space, quite frankly, all the Hilbert space, this is another problem of the Hilbert spaces. If they have a countable base, they're all equivalent to each other. So technically,
You cannot do that just by looking at the Hilbert space itself.
right. So
It's
this
just separable, they're all the same.
is isomorphic. How do you want to make it isomorphic? Like this, like 3. I don't remember what is the symbol, or maybe it's just equal to the space of square integral function. Oops. Of, let's say, R3. There is a unitary transformation that maps from one to the other.
Yeah, so by just looking at the space, no chance. But then I guess we would choose, like, we could distinguish them physically by the knowing what kind of operators do I
Right.
have, like what observables do I have.
Yeah.
So in that case, we would have to start from something which is a position operator,
Yes.
and then find out what is the specific one. I guess this is like, I don't know, is this representation theory, I guess?
This is
Would be
more
the
spectral
tool
theory.
to spectral theory.
I would think that it's connected to spectral theory. Spectral theory is the fact that when you have an operator on a Hilbert space, then you can define the spectra, and the spectra is the more technical term, at least that's my understanding, of what we talk about eigenstates, right?
Yeah.
The position operator does not have a eigenstates, it has a spectrum.
So, for example, naively speaking, I know how many position operators I have for each direction. I see the spectrum is like the full real line.
Yeah.
So, and then I see, okay, so I have 3 commuting operators with the spectrum that is the full line.
Yeah.
So the whole thing is in R3 in a sense. Okay. But I would not get actual like eigenfunctions.
You
I
still
have a
need
spectrum.
something that tells you, and these are all the operators that I have.
Yeah.
You need to have a maximal set of commuting operators. That's basically what you need.
Okay.
Yeah. It's too complicated. And it's the fact that this is so complicated always tells me, like, gives me the feeling somehow it's not the correct characterization. Like the physics is not that complicated, right? So it is true that in physics we do start with a definition of a system, and a definition of a system in part, a lot of the time you define it by saying these are the processes that I have, or these are the observables that I have on my system. These are the things that I can measure, right? And so that procedure I'd be fine with, but the fact that the math becomes so complicated so quickly, that it tells me that there are some details that somehow should already come from the physics, and we're not taking into account of them mathematically in a clean way, and then that creates all the problem.
What if we coarse grain position, or like say we take position to be a element of the rational numbers? Does that fix
Rational numbers are not going to help you, because you still have a dense spectrum. In fact, if you are doing if you're doing measure theory, right, and we essentially are doing, because as I said before, what we care are all the integrals. So you can take the full state, the full space of wave functions, right, and make those wave functions 0 at all the rational numbers. They're still the same wave function, because what you changed is the value of the wave function on a set of measure 0. So what happens on the rationals doesn't matter. It happens like what matters really is what's happening in a, I don't even know how to describe it with a set that it's dense is not enough. It's more than dense. It's I don't know. Well, a set of non-measure zero. I guess maybe that's the right that's the right way. So.
Okay, I see. Like what happens between the rationals?
Yes, which is crazy, right? Because you think, well, what's there between the rational? Well, there are even more, like there are irrational, which are like a lot more than the rational. So this is the problem with infinity. Another question from the chat. I have a question on measurements problem. We postulate some kind of object that causes the collapse of a wave function by interacting with a quantum object. At that and the Schrödinger equation doesn't apply. But the microscopic objects allows also follow quantum mechanics. There is a limit where you get classical and zero uncertainty. They have a small distribution around a classical path. Is there a reason proof? Do they have to be the same thing? A macro object and objects that collapse the wave function. Don't.
The way I understand it is what characterizes objects that make the wave function collapse.
Oh, we have
absolutely. Essentially like the measurement problem, just like what do we consider to be a measurement, right? And there is like open interpretation.
Correct.
Like,
so it's a whole gigantic work. I can tell you how I think about it, and if that makes sense to you. But it's whether we have a proof of this is still all in the work. So the analogy that I always make between measurements is in quantum measurement is between quantum measurements and essentially in thermodynamics when you change the set of possible equilibria, where you change essentially what happens at the boundary, right? So in general, if you think in this sense, like the Schrödinger revolution I was saying before, right, is when let's call it unitary evolution for convenience. Unitary evolution. It's when you have a state that comes in at time t0, and you have a state that comes out at time t1, and really there is a one-to-one map between these two things, and it's when this system is isolated. So there is an assumption of isolation when you are doing a unitary evolution through a Schrödinger equation. Okay, and I can't stress this enough. It's an idealization. Nothing is ever fully isolated, even just because gravitation cannot be isolated. Okay, so this thing is an idealization that never happens. It never happens, right? And then we have our projections, right? That we have something that comes in, psi comes in, and then we have a bunch of possible outputs, psi 1, psi 2, psi 3, and so on, right? And the assumption on the projection is that it's repeatable. So if you do this thing twice, you get exactly the same thing, right? And by the way, the final distribution on this, right, you're going to have a probability 1, probability 2, probability 3, right? The probability distribution that you get at the output depends and only depends, actually the function is like this, on psi. Doesn't depend of anything else, right? And I can't imagine that this is also like I can't imagine that this wouldn't be an idealization too. So for me, these two things are completely two idealized process. One is for processes that are isolated, and one for processes where all the outputs are equilibria. And what do I mean by equilibria? The fact that if I put them again through the process, you get the same thing, right? An equilibrium is exactly an output that if you put it back inside the process, you get the same thing. Right? So these are what these two things are to me. One, an idealized evolution that only happens when the system is absolutely, completely isolated, and that's the Schrödinger equation. And then the other one is where I have a process where all the outputs are equilibria. Okay? And if you think it like that, you say, okay, I have a process and I can get these two things, right? And then you say, does this thing exist only in quantum mechanics? Or we can find other instances in physics where we get the same thing. This is sort of this is exactly the approach that we call reverse physics, right? We go and look at these mathematical rules that we have, and we say, okay, what are they described? Can we find two sentences that tell us physically what these things are describing, and so that we're fully characterized what these things are. And it turns out if you assume that there are quantum states and you ask for an evolution that is completely, fully deterministic and reversible, you get the Schrödinger equation. And if you ask for quantum states, you have a quantum states, and you ask, I want something where all the outputs are equilibria, you have a linear operator that is idempotent. That's a projection. So it's fully, what I uttered in English language, fully characterized mathematically what these things are. Okay? And suddenly we say, okay, now we want to get the physics out. What is this thing? And again, the silly example that I always make is this following. You have a glass of water, and it's an open system, right? So there are molecules that go out of the water, there are molecules that go in the water, and this is going to be if I remember correctly, this is a grand canonical ensemble. Anyway, it's an ensemble that is fully.
Yeah. It is grand canonical.
It is grand canonical. Okay. The name always tells me nothing. So anyway, it's defined by the temperature, by now I'm getting confused, by the grand canonical
Chemical potential.
Chemical potential.
And
it's pressure. It's pressure or volume?
Pressure or volume, yeah.
I don't remember which one. Well, let's say volume. I don't remember whether it's pressure.
Yeah, I think so.
So let's say it's volume, right? Okay, so what happens is that the number of particles, it's not well defined. The number of particles keeps fluctuating. And since we're describing an equilibria, the equilibria in terms of a number of particles is a probability distribution of the possible values. It's a statistical quantity. You don't have a full quantity. But the chemical potential is instead fixed. In effect, the role of chemical potential is telling you what to characterize the fluctuations that you have in terms of the number of particles. Okay, and now you want to say, but now I want a state where the number of particles is fully defined, and it's that thing such that it doesn't change throughout the evolution, right? Then what you do, you close the lid. So you have this and you close it. And if you close it, now you change the type of ensemble. You went from grand canonical to canonical. You still have the temperature and the volume well defined. And now you're going to have the number of particles well defined. And the chemical potential is not going to be well defined anymore, because the chemical potential is there to, again, tell you about fluctuations of number of particles. The particles are not fluctuating. You don't have any chemical potential. It's fixed. And of course, when you close the lid, the number of particles that you have trapped inside depended on the number, the random fluctuation that you could have had, right? So you're going to have the output actually is going to be a series of possible canonical ensemble, each with a different number of particles, right? And each of them with a probability distribution that depends on what was the chemical potential before, right? So this distribution is going to be fully determined by the previous variable. And again, this is in equilibrium, right? So if we close the lid again, right, we call this twice, we get the same thing, right? So if we had one particle and one number of particles, you could get one. If you get in two and two, right? So this is very similar to that thing. You have a set of variables that are well defined beforehand. Let's say you are an eigenstate of those variables. Then you do something, you act on the system, you have something that increases the entropy and puts you in a probability distribution over another set of possible equilibria, which is exactly what would happen if you have, you prepared spin up, now you go measure and you want to know whether you have spin left or spin right, right? You do something here that it's sort of interacts with the system strongly, and then you get your probability distribution of P left and P right. So this is how I think about it. And the way that this makes sense is that there is already a lot of body of literature that tell you that measurements are transition from a metastable state to a stable state. So let's say that you have a wire chamber. What is a wire chamber? A wire chamber is a series of wires where there is electric charge, right? All distributed here, right? Such that when there is a little charge that comes through, it perturbs the system, and now the charge is going to go in both directions. It's going to get absorbed at the two ends. By knowing the difference in time that go from one end to the other, you're able to say, okay, this is the position where the particle went. So it's you had a metastable state. You have the state that was in equilibrium, but you just needed just a little tiny bit to perturb that equilibrium and go to another equilibrium, and that's how you make the measurement. A bubble chamber is sort of the same thing. You have this saturated gas, a particle comes in and then makes things coalesce. And there are a lot of people from the experimental side that tell you that's what measurements are. Measurements are things that go from a metastable state to a stable state. So what I did in sort of in math here corresponds to that point of view. Now, do I have everything 100% worked out such that I can prove beyond the unreasonable doubt that this is the only way to think about it and we should just do it like this? No. Maybe in 10 years I will have it, not right now, but this is how I think about it. And the other reason why I think about it like this is because it gives me good intuition. So when I'm looking at an experiment and I'm thinking about the math and I'm thinking about the physics, what happens in the experiment, I can map those things more quickly when I think about it in these terms.
So just to connect this to what Lorenzo was asking about, like I think he also wanted to see specifically in like standard quantum mechanics, how is it possible that if I have like a big system that is like evolving unitarily, how can it be that I have some kind of collapse? And then what is like big enough, I guess, to cause this kind of collapse, right? So I think so. First of all, usually what people do, for example, in like many worlds or whatever, they explicitly extend the state to include like an environment. Then you can have actually pure evolution, like a unitary evolution, sorry, of a pure state of the global system. And when you look at the subsystem and you would, I guess, trace it out, you could get a mixed state in the system you want to measure, right? So, for example, if you would just have a spin measurement, you don't even need like a full environment. You will only need to like distinguish the position of the particle and its spin. If you send it through like a specific magnet, you would get like a entanglement between position up, and position down, spin down. right? And if you only look at the spin, then you can consider this to be like a mixed state, like probability half up, probability half down, if that makes sense.
Yeah, what you're trying to do there, which is this, you're basically saying, well, it's this, but you want to say that it's secretly you have some kind of Schrödinger evolution.
Yeah, I think this is what you wanted to see. How does it
Yeah.
even
That
fit
cannot
together?
work.
Like,
That cannot work.
so there is no collapse because you get a mixed state, and then it still needs to collapse, and like you have to choose one of the results, right? Up or down. But to me, this would be just like updating probabilities, like a Bayesian update of my description of the system. Does it make sense?
It can't be just updating because of the quantum Zeno effect, right? So quantum Zeno effect, if you have something there and you keep measuring it, you slow down the rate of evolution. Like you really are acting, you are doing something. So you can't just say, oh, the projection is just some update. No, it's a physical process. It's a physical process that is doing something. And so
But like partly only, right? Isn't the physical part the thing that ensures that you are that you have some kind of mixed state over the eigenstates of your observable? Isn't that the physical part that is happening or not?
no, because you're reprojecting the thing into the original state, right? So like you really have.
So you had the picture of like let's say you have a simple system which is just like on two-dimensional, so you're on a Bloch sphere. Then depending on your observable, your state has to kind of collapse onto one line, which is defined by your observable. Isn't that the non-unitary evolution that is the actual physical thing that is happening?
Right. So
And then you just find out what the actual value is, and then this is where the jump happens to whatever you measured, up or down. Does that make sense?
So your Schrödinger evolution can only move things on the surface, right? Because it can only move a pure state to a pure state.
Yeah.
Okay. The projection operator instead takes things and moves them on your axis.
Well, the projection operator would actually either project me to the top or the bottom, right?
That's the issue. Projecting to the top on the bottom, that's the Bayesian part. If I'm here, if I have a mixture of up and down, I look at things, then I'm going from a point on the axis to here or here, to the two extremes.
Yeah, but this is really like a Bayesian update and not the physical process.
That's just the Bayesian update. Yes.
Okay. Yes.
That's the Bayesian update. The going from here to here, that's a process that has to increase the entropy. That's not a Bayesian update.
Absolutely. That's exactly what my intuition was. And I was just saying this collapse onto the line, this physical process, isn't it possible to describe this as a unitary evolution on a bigger system, including the environment, where I just trace out the environment in some sense?
That's exactly what Lorenzo is also saying.
I think so. That's what he was getting at.
He has, if we consider the whole system, it's isolated and should evolve unitarily, right? That's the core of the issue. Can you describe any process increasing entropy as something that happens with a bigger system, right?
Yeah, and that's the question.
That's the question. No? That it's not unique to quantum mechanics as well. It's the same thing in classical mechanics. In classical mechanics, you have this problem that you say, okay, I have a box of gas and I have a bunch of particles, and this is at a particular entropy. And then I assume, oh, but the thing is fully deterministic and reversible, so I have a Hamiltonian, right? And I have a Hamiltonian evolution, so I have, my dq dt is equal my partial h partial p, right? And I put this in, and then I want to say the gas is evolving through Hamiltonian evolution, and it reaches equilibrium. Hamiltonian evolution conserves the entropy. So you can't do that. And then you say, okay, well, what about if I talk that there is the universe, and the universe is actually interacting with my isolated system to make it go to equilibrium, right? It's the same problem.
I agree. But do we also agree that this is possible to describe it like that?
Yeah, but then you're going to have the same problem on the bigger system.
Yeah, I mean, maybe I don't care whether I can describe this in a big picture using deterministic and reversible evolution or unitary evolution.
To me is
I just want to see if it's possible.
So it's everything is going to be possible because you can always take something that it's random and add enough hidden variables to make it not random, or something that it's absolutely deterministic and reversible and add some other variables that are evolving non-deterministically. Like you can always do that mathematically. The problem is why do you want to do it? What is it that you're trying to take out of this? So I think the issue is this. You want to say the underlying motive to me is that you want to say that this isolated evolution is the real thing.
Yeah, that's true. We want some kind of real modeling of what is happening. I agree.
So if you want to say, I have two different things and I want one to be real, the easiest thing is to take this one as the real one. Because from this, you can actually get the isolation in the limit quite cleanly.
Yeah, I think actually this is more like a metaphysically interesting question.
This is
and it's just
metaphysics, yeah.
Yes, so I'm not saying like when I talk only about physics, then I inherently need the real picture underlying everything.
Right.
I wouldn't do that. It's just metaphysically, for my own philosophy. Maybe I want to just see if it's even possible to keep some kind of real picture of what is going on. And I think, yeah, we're explaining that it should be possible in principle.
Yeah. Okay, first, Lorenzo, are we actually hitting the problems that you are asking, or we're still far? Let me know in the chat. There might be a delay. Okay, so but this description of the whole system does not include the clock. Yeah, okay, so this is kind of how I look at it. And again, there might be a lot of people that are not going to agree with me. But the point then becomes, can I make, is it reasonable for me to even want to have this picture as the correct fundamental one? Or maybe that's the wrong thing. Like my insistence of having such a picture underneath is actually preventing me to understand the physics, right? Like, how do you know? Like, what is the impetus to say, oh, that must be the real picture? Because at the end of the day, what we have in physics in practice, there are just a bunch of models that we use in different cases. And there is no sense that one model is better than the other. So I can use the same quantum state to describe a single particle, or to describe a complex object like a complex molecule that has hundreds of parts. And I do diffraction interference experiment. I use the same equations. I use the same model, right? So since I already know that I use the same model that I use for the more fundamental objects, also for complex objects, why should I be bothered that is just a model approximation? It doesn't describe the whole reality. This is something that I quite frankly do not understand, because I don't have that impetus. So if Tobias, you have the impetus, if Lorenzo, if you
No,
have the
it is really just from like classical physics. It is just this, I don't know, when they realized that when they thought they could describe the whole universe, everything that's happening, just tell me position and velocity
right.
of all the particles, I can't predict anything. We are kind of still on the hype train and like, oh, this is so great. We want to keep it. But it's just metaphysically, I don't know, preferable to some people. I totally agree that our approach is like, I guess you would call it instrumentalist.
No, it's not
Like
instrumentalist either, because instrumentalists
I
go
don't
and
know,
say everything that makes no sense.
I don't know exactly, but it's like we focus only on what is empirically doable. We only want to
And the
describe that.
models. So the thing that is important to me is that these are models and they're valid only in a specific set of circumstances. And so I shouldn't be bothered that they're not valid everywhere, because they're models and their idealization that are valid only when the idealization applies, and if idealization doesn't apply, it doesn't work. So for example, Magma says a personally view the collapse as becoming entangled to the system. Okay. Like keeping two things entangled experimentally is really, really hard, right? So yes, we are able to take two photons and entangle them and say ship them under kilometers and so on. But it's not that simple. So the whole idea of having an entangled system, that you have this correlation, then you verify that you have this correlation, it's something that we work really, really hard to do. Even the Schrodinger equation, right? The fact of having this isolated system and evolve unitarily and so on. Experimentally, you have to keep your system coherent. It's really hard to do. It's not something that just comes naturally. If it came natural, that things can remain coherent and entangled all the time, we would have noticed these things, 10,000 years ago. The fact is that it's not. Like, you need to create a setup that, again, creates this level of isolation such that these models are actually useful and can actually be actualized. So so if this is the case, right, then I really don't see, and again, it might be my problem because a lot of people want this, but I don't really see why you would even want to try to talk about it in these terms. Because even if you say, okay, I want to have a complete picture of what's going on, that's fine, that I can understand, but it has to be on things and with processes that, I don't know, that are very stable, are things that keep, that are very natural, they're very stable and so on, not these very sophisticated things that we do in a lab to make some of these effects come out. Like, is it really the case that the whole of nature functions at a deep level on these processes that are then so hard to expose? It seems so counterintuitive to me.
I think it's like usually you expect this to be because your environment interacts with the system that you're studying, right? But if you really want like a real picture of the whole universe, what is the environment that could mess up your system? It is the full system. I imagine I'm like some abstract godlike being that can just observe everything without interfering.
Yeah,
So
so
yeah,
this is the other people. So we said that these are equilibria. These processes are equilibria. Equilibria and states in general have a time scale, and they have a spatial scales, and these two things have to be connected. So when I talk about temperature, the temperature exists only because there are a certain amount of fluctuations that go on for a finite period of time. If I take this, the one single microstate at a specific time t, I do not know what the temperature is. I'm going to have the energy at that time t, but the temperature is not just that energy. The temperature is how the energy is fluctuating, right? So if I go back in quantum mechanics, right, then and I notice that all my states are statistical, right? If they're statistical and describing the statistical quantity, it is because there is sort of a minimum time interval in which those make sense because I'm getting statistics. So there has to be a time, and the state has to be essentially well defined within delta t and be the same thing in that delta t such that all the statistical quantities are well defined, right? So it's like this, right? If I want to talk about a box with a specific temperature, this whole thing has to be in equilibrium. Otherwise, I can't talk about that temperature. And so if I have little pieces, then I could say, okay, those are now my new equilibria and talk about in terms of those things. So now when I have my single particle, my single electron, I have to say, okay, this thing is in some kind of equilibria because for that particular delta t, there's going to be interaction with the outside, right? Because it's not going to be completely isolated. But I can remove those interactions, and that's when I can talk about my electron and my wave function. So if this is the way that it works, so when I talk about a wave function, the wave function is sort of the stable part, which includes already the possible fluctuation with the environment. And when I redefine the system, I'm going to have different types of fluctuation for and so on. So if this is the case, which seems to be a lot more physical to me, then the wave function is not the snapshot of a God view of the world, because it includes all the possible fluctuation, because I need to be able to repeat that experiment multiple times. And so it's not just one shot, it's all the possible God's view that the God would have in that case, a God person would have in that case, that keep my average is the same. So, but this is, again, this
I
goes
agree.
very much into metaphysics. And I think there is a distinct thing, let's say, between an ontological metaphysics that basically tells you the God's view of the world, and a more epistemic metaphysics that tells you what are the attributes of the system that we can prepare in the lab, right? Because we have some practical requirements to fulfill. And it doesn't seem to me that the two have to coincide.
I agree. So I mean that would be like so yeah, in general, I was saying if you want like the real view, you just want that for metaphysical reasons. But then I would also agree that picking the wave function to be real is not really, I don't know, to me this is not doesn't seem to be a sensible choice. But lots of people do that. I don't know.
Yeah, so as I said, there are some things, because I've been talking about these things with a lot of philosophers, and I don't understand why. Like, I understand more on their point, like they stated, but I want to have some kind of real view, as you're saying, Tobias, right? That they want to have that. And to me, it's like, well, physics is not going to give that to you. It's only going to give you the epistemically accessible part. So all the all the objects that physics gives you are tainted. Because all the objects that physics gives you are just going to be the objects that you can do science of, so they're not going to be ontological. Like they are tainted. Like they have the requirement that you can get the information in and out. So yeah, I don't know. I don't have the language to verbalize this correctly. Anyway, but yeah, this is not mathematical foundation. We went way outside of the realm of things that I think we can have stable answers. I guess that's kind of my problem. The reason why I get frustrated with some of these conversations, that one, they have this flavor. Like, I want to be able to say some things, and I just want to be able to talk about only the things that I can talk about in the math and in the physics, and that's it. So everything else that I can take out, I'd rather take it out and make progress on things. Okay, so Magma says, my reason is that superposition collapses very easily because they can interact very easily, and it is difficult to make things interact without anticipating causing more things interact. But again, if the superpositions, so superpositions, first of all, are just other states. Like, there are no states and superpositions; they're just states. And the entanglement is a little bit different, because entangled states are particular type of states. But the point is that I'm trying to make, it's like a category error, putting your cart before your horses type of thing. Is if superposition and entanglement are there to describe some type of reproducible things that we can make in a lab and so on, it doesn't necessarily seem to me that those are the things that I can put at the foundation of everything else. I need to be able to say this in a much more polished way. I'm not able to. And Lorenzo says, of course, actually describing the whole system is this way is not practical, but in principle, well, at least it made sense. Okay, good. But in principle, it evolves unitarily. Then the collapse seems to be simplification to not do that, not a physical problem. So, like, my sense is that you can actually much more easily say that the unitary evolution is a series of collapses than say that the collapse is actually a unitary evolution. So this is how it works, and it's extremely simple. Actually, let's give you a physical picture. So let's say that I have a polarizer up, like a polarizer up, and a polarizer that is horizontal, right? So I send a particle here, and let's say for sake of argument, it's polarized and now it's up. And actually, I already prepare up. Let's say that I already prepare up. After up, it remains up, and now it's going to become left of right with 50%. Okay? I can put a polarizer that it's 45 degrees. And I do the same thing. It's going to be up, it's going to be here, and then I go, and it's going to be horizontal. Now, the probability that I'm going to the right is going to be greater than I have the probability to the left, because I can make the jump a little bit smaller. And you can repeat this again. You can put something in the middle, right? And something in the middle like this. And if you put infinitely many, you're going to have that the thing just rotates, and you end up with 100% probability coming to the right. So the point is that you can see unitary evolution as an infinitesimal series of collapses. Now you say, I can accept to not have the unit evolution. So if you say this, like if you say, this is just math, and actually physics, because you're actually doing in a lab. But yeah, it's a trick. Can you say now that this unitary evolution is from a physical sense, can you make an argument that unitary evolution is a series of collapses? And here you can make the same argument that you can make in thermodynamics. In thermodynamics, you say, I have a process, I start with an equilibrium state, and I have a final state that it's an equilibrium, right? And then you do the quasi-static evolution. What is a quasi-static evolution? Well, you go from one equilibrium state to the other, and you assume that at every point you're in equilibrium, and you're making small changes. And that's how you have quasi-static evolution in thermodynamics. With the same thing, you can turn your projections in terms of unitary evolution. And so you say, the fundamental thing is that in physics, I need some states of equilibrium. That's the thing that you need. And you always have them. And then you have ways to go from one equilibrium to the other. And those are the black boxes. All your projections are the black boxes. And then the special case is when you connect enough black boxes in a way that you have deterministic and reversible evolution, and you have unitary evolution. So that's the way that I would solve the problem. And of course, if you want to have a realistic pictures, you're not going to be satisfied because you're saying, well, you're saying that at fundamental level, I don't know anything, because you're saying at the fundamental level, everything is black boxes, right? So it's absolutely unsatisfying to the realist, but to me, it connects to thermodynamics, it does all the things. And so this is the part that I'm trying to also more formalize mathematically and see if we can make a general case. I think I will make a video. So I think I should be making a video about this inverse measurement problem.
So I think there is a real problem connected to that, which is our approach was like to extend the system to like a bigger system, basically.
Yeah.
And in quantum mechanics, you always have like a choice of where to cut, right? So we usually only model the smallest part necessary as actually quantum mechanical, and we don't include everything else that is like not necessary, right? Because it would be unnecessarily complicated. So we do need to check that this doesn't make a difference, right? So if I extend my system to include the environment, I should make sure that this doesn't change my predictions, right?
Yeah, and you also have
just one more thing.
Go ahead.
The environment specifically includes like the measurement device.
Exactly what I was going to say.
I need to be able to model what the measurement device is doing. Otherwise, how do I know that it's working?
Yeah.
So that's, I think, the physically important part that is connected to that.
Yeah. So you hit that. This is what I was going to say. There is an assumption in physics that the measurement device is independent of the thing that you're measuring. Like you need to be able to make these preparations in a way that it's independent. And if you're starting to put everything together, you're starting to lose that issue, that feature, and then I don't know what you're talking about anymore. Yeah. Anyway, it's the hour and a half. I don't know if this was more useful, more interesting than usual. We did have more participation in the comment, which is nice. Thank you to everybody to participate. If there are other questions, I'm happy to stay for another like 10 minutes, but then I think I probably have to go and prepare lunch that I'm getting hungry. So.
Yeah, I think that was very interesting, but I think we went a bit all over the place.
Yeah, we went a little bit over the place.
I'm not sure if I don't know, if Robert had some kind of technical questions. I'm afraid he might be more confused.
No.
Yeah, after that discussion, I'm a bit confused. But I did have a thought about the measurement problem. Like part of why it's confusing is we think like, oh, quantum mechanical systems are constantly interacting with things, and why, like, if it's interacting with something and it's not a measurement that we're picking up on, like, why is that not collapsing the wave function? Whereas when it's the interaction that we do specifically do with it, then it is. And I think maybe the wave function is part of the issue is it's not like the physical thing. It's just like what we know about it.
Yeah, so that there is this idea that the wave function is just the information, but again, there is the issue that things like the Zeno effect, you do have some effects that then correspond to actual physical processes. So you start running into a bunch of other problems. The other issue also that with this idea that measurements are always things that makes things collapse, that might also not be technically true. So I was talking to, oh, geez, this was like 6 years ago. There's this wonderful conference that I'm actually going to go next month in Turin that it's on quantum foundation, but there are a lot of people that are experimentalists and they do metrology and so on. And talking to one was telling me that there are some situation in which you can make measurements on a collection of particles and get data out without actually causing any significant collapse or things like that. And this was just one guy that was telling me, and I don't have sources and so on, so take it with a grain of salt. But I also think that there is in the way that people interpret quantum mechanics and measurements and so on, there is a too strict a thing that measurements of are collapses and all collapses are measurements. And I don't think that's so. Some collapses are actual processes. As I said, quantum's in effect. You can measure it. There is something going on, and even if you didn't go and update your knowledge with the result of the measurement, you're still doing something. So, so you're actually causing something. And then there are things like temperature, which are quantities, but there is no temperature operator. Like you do not collapse the wave function for in an eigenstate of temperature. There is no eigenstate of temperature. It's because the temperature is a parameter of a mixed state. So you have a bunch of mixed states, and they're all parameterized by temperature, and then you go and you measure that parameter. And so this is another reason why maybe I should cut all this discussion earlier and say let's stick to the math, but yeah. So I hope it was useful and interesting anyway, Rob.
Yeah, it's always a pleasure to talk to you. So thanks for having me on.
Thank you for coming. And again, if other people have other more technical questions on the math and want to come and discuss, I'm happy to repeat this again. So, okay, we close it here. Thank you, Rob, for sort of essentially initiating this by coming and asking questions. Thanks to Tobias as usual. Thanks Mars, Magma, and Lorenzo for the participation and memes of distraction. And I won't be here for the next month because I'm going to be on travel. So I think we're going to repeat, well, I might send an announcement on the YouTube channel. I think it's going to be in either end of May or beginning of June when we're going to repeat this. Bye, everybody.
Okay. Bye.
Bye-bye.